Look closely at the central dancer in this mid-air spin. Notice how the body turns entirely around a single, invisible point in space. The dancer changes the direction they are facing, but their physical size and shape remain exactly the same. In geometry, this specific type of movement is called a rotation. We see the exact same principle at work on the road. The front wheel of this motorcycle is in constant rotation. Every spoke and tread turns continuously, anchored by a fixed pivot point at the axle's center. On a grid, this regular hexagon completes a full 360-degree rotation. It perfectly overlaps its outline 6 times, giving it an order of rotational symmetry of 6. Spun through the same path, the letter Z only matches its outlines twice. Its order is 2. Whether a shape matches its outline 6 times, twice, or only when it finishes the spin, the ruling law of rotation remains constant. The final image is perfectly congruent to the original object. The side lengths, the interior angles, and the total area never change. To accurately describe a mathematical rotation, you need 3 pieces of information: the center pivot point, the exact angle, and the direction of travel. Direction is divided into 2 paths. Clockwise follows the 12 to 3 to 6 sequence of the hands on this clock. Anti-clockwise moves in the reverse direction. Let's test this manually on the grid with triangle PQR. We want to rotate it 90 degrees clockwise around the origin, 0, 0. If we place a sheet of tracing paper over the shape, anchor it with a pin precisely at the origin, and swing the paper 1/4 turn to the right, we find the exact location of our new image. But we don't need the tracing paper. We can bypass manual work using a coordinate shortcut. For a 90-degree clockwise rotation around the origin, you simply take your original x and y coordinates, swap their positions, and flip the sign of the new y value. Let's see if you can apply a similar rule. Try to find the new coordinates if we rotate point P at 3, 4 precisely 180 degrees around the origin. The new point sits at -3, -4. A 180-degree rotation is the simplest shortcut of all. You leave the coordinates in the same order and just flip both of their signs. Look at these 2 triangles on the grid. We know the original object and we can clearly see the rotated image, but the pivot point is missing and it is obviously not at the origin. We have to reverse engineer the rotation to find it. We start by picking one vertex on the original shape, point A, and drawing a straight line to its corresponding twin on the image, A'. The true center of rotation must lie at equal distance from both points. That means it sits somewhere along a line that cuts exactly through the middle of our A to A' path at a 90-degree angle. This is called a perpendicular bisector. To pinpoint the exact location along that bisector, we need a cross-reference. We repeat the process for a second pair of corresponding vertices, connecting point B to B'. Then we draw the perpendicular bisector for this new path. We now have 2 distinct lines of evidence cutting across the grid. Where those 2 bisectors cross is your exact center of rotation. Every single point on the shape pivoted perfectly around this specific coordinate. By isolating the geometric midpoints of the object's travel path, we replace guesswork with mathematical proof, locating the true anchor point of any rotational system. If an object turns 90 degrees clockwise, then rotates another 180 degrees around the same center, these compound rotations add together. This 270-degree clockwise turn places the shape in the exact position as a 90-degree anti-clockwise turn. To describe a rotation, state its center, angle, and direction. Always verify congruence. Side lengths, angles, and area remain identical. For shortcuts around the origin, flip both signs for 180 degrees, or swap values and flip the new y sign for 90 degrees clockwise. Rotation is about shifting your perspective. The object maintains its exact proportions and structural truth. It just faces a different direction on the grid. Find your pivot point, apply your angle, and make the turn.